Hello everyone, how's life? So I expect that you all are doing well, and today is going to be basically a continuation from where we left in the previous video. Now in today's lecture we are initially going to kick off by understanding how to calculate or rather I should say how to calculate the number of eye centers. Let's say we have got a complex mechanism which has 4 links, 6 links or whatever, say n number of links. Is there a formula which can let us know to calculate the number of links? Number one. Then secondly, we'll also try to work out the different kinds of eye centers, because there are some eye centers which are going to be fixed, some are going to be permanent, and some are going to be neither fixed nor permanent. All of this and much more coming up in today's session. So let's kick off first of all by understanding how we can actually work out the number of eye centers. So just try to read this number of eye centers. It is the number of possible combinations of two links. Okay, it is the number of possible combinations of two links. You can also perceive this in a different manner. You can also say that the number of instantaneous centers is the number of different combination of n links taken two at a time. Number of different combinations of n links. Here n basically means the number of links. So number of combinations of n links taken two at a time. You just have to go into flashback, and this is something which you've actually learned in permutations and combination. This was earlier expressed as NCR. So NC2 can be simplified, and this is what exactly work out. Okay, so this is exactly how you can actually calculate the number of eye centers. Let us take up this case, and this essentially is what you refer to as a 4-bar mechanism, isn't it? And for a 4-bar mechanism, let us first of all try to calculate the number of eye centers. So if you watch carefully, there are 4 links. This is going to be link 1, link 2, this is link 3 and link 4. Okay. Now, can you get me the total number of eye centers? So just punch in the value n as 4 minus 1 by 2, and this is going to be 3 by 2, and this is 4 3 is 12, 12 by 2 is obviously going to be 6. So we know very well that for a 4-bar mechanism or a link or a mechanism having 4 links, the number of eye centers is 6, right? And right now what I'll try to do is I'll let you know which of those eye centers come in this category, fixed, which of those eye centers fall in permanent category, and which of the eye centers do not fall in the first 2 categories, that is the third category itself. Okay, so just take a look at this. We know very well, and by the way, let me make a protocol. Small n is for the number of links, whereas capital N is the number of instantaneous centers. So let's take a careful look at this. Okay, I've got to rub a bit of stuff, Okay, let me rub this. So for a 4-bar mechanism, the thing that we already know is that the number of instantaneous center is going to be 6, right? How to locate all the instantaneous centers? Well, you've got to wait for at least 5 to 10 minutes more, because that will be taken up in this article. But before that, you just have to trust me that with the help of inspection, eye centers can be located. And this is going to be I12, isn't it? This is going to be I14. This is going to be I23, okay, 2 and 3, and this is 3 and 4, and that's why this is going to be 3, 4. This is just by visual inspection, right? I'll talk in detail about that in the guidelines which I'll try to give you in this article, the general procedure. So which of the eye centers are fixed? So if you just take a careful look, eye center I12 and 14, okay, they will remain in the same place for all configuration. Does not matter where this link goes, towards the anti-clockwise direction or towards the clockwise direction. It makes no difference to the eye centers 12 and 14. Hence, these 2 eye centers, that is I12 and I24, these are fixed. No matter how the configuration changes, how the links move and change, it makes no difference to these 2 eye centers. That means they are fixed. They are not going to change their positions whatsoever the mechanism moves. Second, we are going to talk about the permanent eye centers. So why are they permanent? First of all, let me just tell you, the permanent eye centers are in the form of I23, and why are they called as permanent? There is a specific reason. 2, 3 and 3, 4. Okay, let us try to read this. They move when the mechanism moves. Now these eye centers are such Now let's say that the mechanism reaches here. Okay, in that case, this I23 will change its position, isn't it? Right? And I34 will also change its position. So it is changing position, it is moving with respect to the mechanism. And why has it been named as permanent? Because this joint, guys, this joint is actually permanent. That's why this joint is permanent. That's why it has been named as a permanent eye center. And over here we have a pin, right? And the center of that pin is the eye center 2, 3. You can say this. Okay. So that was all about permanent eye centers, and that was all about fixed eye centers, and both of them can be easily located with the help of simple visualization by inspection only. Now I'm going to talk about this very important eye center, and something without which the problems cannot be solved. Okay, this is a bit tricky, and again I'll let you know all of that in detail in this section, in this article, right? Okay, so these actually vary with configuration of the mechanism. What are those? First of all, let me tell you, let me draw that rather, and let me just make something like this. There is going to be one eye center over here, and another eye center is going to be, let me just produce this. Okay, so there is going to be an eye center over here and here. These two eye centers are neither fixed or nor permanent. How will we do the naming? Well, that is something that I'll let you know. But these two eye centers are what? These are neither fixed nor permanent. They are going to vary with the mechanism, when the mechanism moves. Okay, now let us take this session forward, and now let us try to understand the method for locating the eye centers. Here we go. Method for locating eye centers. First of all, we are going to talk about a turning pair. So just keep on watching turning, whatever it is, Turing. It's a turning pair. Okay. So what would you call a turning pair? It's something like this. Let's say this is our link 1. Let me just write this as link 1. There is a joint and there is another link. Let's say this is going to be called as link 2. Right? Now, this is link 1, this is link 2. Wherever they intersect, or this is the joint, okay, and the joint is the eye center. So this is going to be called as eye center I12. So the link 1 and link 2, it forms a turning pair. Okay, they can move with respect to each other. Their point of intersection or their joint is the eye center. Let me just write this conclusion. Joint is the eye center. So that was all about turning pair, right? And it's, if you try to visualize this, let me try to make this if I can. And this is exactly what I wanted to draw. So these are two links. So this is the axis of rotation, you can say, axis of rotation, and this is the top view. In the top view, this is the instantaneous center of rotation, you can say this. Now let us take this session forward, and the next pair that we are going to talk about is the rolling pair. Okay, and this is something which I had introduced in the first video, first lecture, rolling pair. So there is an object which is going to roll above a horizontal surface. So just take a look at this, and you will try to understand in the very, very, very easy manner. So there is an object, let's say a disk. Let's name this disk as link 2, and there is a surface like this, and this is link 1. Okay, link 1 is fixed. Link 1 is going to be fixed. Now if you watch carefully, let me just mark 2 points, and this obviously is going to have a center. Let me mark 2 points. Let's say this is A, another point, let's say this is B. Okay, now A, the net velocity on A, and if I can just make it this way, this is moving in the anti-clockwise sense. The net velocity on A is in this direction. Let's call this as V A. Just a second. So guys, very sorry for the interruption. There was a power cut and there was only one LED tube light functioning, and that too because of the inverter. Now all of them are back, and let's get back to business. So I was talking about a disk which was actually rolling. So this disk, let's say, is link 2, and this surface over here, let's say ground, is link 1. Now obviously velocity at point A is going to be in this direction, and point B will be somewhere along this direction, let's say VB. If we just try to work out, we can draw a perpendicular, it would be something like this, and draw a perpendicular to with respect to this velocity. Both of them actually intersect at this point. Okay, and this is the I center, I12, and in case of a rolling pair, the I center is right at the point of contact. Okay, it's as easy. Okay, so these two have been covered. Now let us talk about another one, and this is what is known as a sliding pair. So just have a careful look at this sliding pair. Okay, sliding pair. So one link, we are going to keep it fixed. Let's say something like this. The scenario is like this, and then there is a link over here. Let's call this as link 2, and let's say this is link 1, and link 1 is actually fixed. Okay, so the motion, let me talk about 2 points, right? What can you say? What can you comment about the instantaneous centers? If you see, these two are slightly inclined, and if they are inclined, obviously their perpendiculars are obviously going to intersect at some point. Okay, the distance could be large, but they will for sure intersect. But in this case, the direction of velocity is absolutely parallel. This is going to be called as VA, and this is going to be called as VB. And if you try to draw a perpendicular to this, it would be something like this. And if you try to draw a perpendicular to B, it would be something like this. So what you have to say is that the instantaneous center of link 1, 2, I12 is at infinity. Okay, the concept is something like this. If you can have a circle, okay, let's make one circle, small circle. So this curved path, if you make it bigger, then this curved path will slightly flatten. If you make a much more bigger circle, this will much more bigger circle like this, it will keep on flattening. So what you can say is that this over here, the I center is at infinity. Okay, the I center is somewhere here of a circle, this bigger circle I'm talking about, whose radius is infinity. So this is basically a way to perceive how a block slides over another link, right? One more way of looking at this is with the help of math, and let me tell you. So with respect to an I center, the link is actually in the course of pure rotation. We know that very well. So if you just take a look at this, we know very well that V equals omega R. That's quite true. And R basically is the distance of the I center. Okay, V over omega. Now we know very well, both of them, these both are linear velocities. There is absolutely no angular velocities. Okay, that means this is going to be 0. If there is no angular velocity, then if in the denominator we have a term as 0, then obviously this R will tend to infinity. So this is also a logic with which you can perceive. Just to remember one thing, if one object is sliding over another, in case of a piston motion, obviously the instantaneous center will be at infinity. Okay, if this is the direction of velocity of the piston, the instantaneous center will be perpendicular in this direction. Instantaneous center at infinity. Remember this, and all your problems will become very easy. Okay, now sliding pair, as I told you, there are 3 cases. This is the first case on a horizontal surface. The second case of a sliding pair is on a concave surface. So just take a look at this. This is also very interesting. Surface is something of this sort. Let's call this as link 1, and above this there is a body. Let's call this as link 2, and now let me make 2 points, and let's say this is traveling in this direction. So obviously, and let me just, this is the direction of velocity of one point, let's say A, and this is the direction of velocity of another point, let's say B. If you just try to make lines perpendicular to this direction of velocities from here also, perpendicular to the direction of velocities. They're going to intersect somewhere. This is I center 1, 2, and this basically is the center of curvature. Okay, this can be perceived in the different sense also. In a concave, just like in a concave surface, we can actually interpret this on a convex surface. On a convex surface, it's very easy. Okay, it's going to be something like this and like this. Okay, let's say this is moving in this direction, so this way, and they are going to converge somewhere. So obviously this is the eye center. If this is linked 2 and this is fixed over here, this is eye center 1, 2, and this is the center of curvature. Center of curvature. Now let us try to summarize everything. For a turning pair, the eye center is at the joint. Remember this. Second, for a rolling pair, the eye center is at the point of contact. For a sliding pair, the eye center is at infinity. For a sliding pair on a concave surface, the eye center is at the center of curvature. For a sliding pair on a convex surface, again here also the eye center is on the center of curvature. That's for sure. Now let us talk about the third section, that is Kennedy's theorem. Very important. Okay. So just take a look at the statement, and this is the statement given by Arnold Kennedy. Very important, and this is actually associated with 3 links, 3 bodies or 3 members which are connected to each other and sort of are going to move. So if 3 bodies move relative to each other, they have got 3 eye centers, fine, and all of them lie on a straight line. Well, if you just try to think about this, all the eye centers are going to lie in a straight line. Is this true? Let us try to work it out. So what I'll try to do is, let me take 3 links into consideration. Yeah, something like this, and one more this way. Okay, let's keep this link as fixed. Okay, let's keep this as fixed. Let's call this as 1, let's call this as 2, and let's say this is 3, and let's say this point is marked as B, simply B. So if you just talk about the permanent eye centers, okay, a fixed eye centers, it would be something like this. This is going to be I23, right? I23, not 2, 3, but 1, 2. What am I writing? This over here, 1 and 2. This is going to be I12. This is going to be I13, and over here, this is also can be located very easily. This is going to be I23. Okay. What is this? This is a permanent. Because of a permanent joint, this is a permanent eye center, and these two are rather fixed. Now, if you just watch carefully, this will not lie on a straight line with joining I2 and I13. But Kennedy's theorem says that if 3 links are connected and they move relative to each other, then all of them, their eye centers, the 3 eye centers are going to lie on a straight line. Let's try to take a look at this from a different perspective. Condition 1. Let me just write this. Condition 1. In condition 1, what we'll try to do is we'll try to consider this I23 on or as a part of link 2. Okay. If I23 is on link 2, just take a careful look at this. Then the velocity's direction would be somewhat like this. This is the velocity at point B, isn't it? And this is going to be perpendicular, obviously. Okay, then what you can say or you can conclude is that VB is going to be perpendicular to the line joining I12, I13, that's for sure. Let us take a look at another condition. This is condition 2. Condition 2. Now in condition 2, what we'll try to do is we'll consider this eye center, I23, on this link 3. Okay. Now this is a common eye center. So this common eye center is for link 2 as well as link 3 for sure. This is the fundamental of eye centers. So I23, now let us consider it on link 3. Very interesting case. Now if you consider this eye center to be on link 3, then the direction of velocity will be in this direction. this is going to be the direction of VB, perpendicular, isn't it? Very strange. How can the velocity have same magnitude but different directions at any instant of time? This is not possible. This is not possible. So the conclusion is velocity cannot have two different directions. So here is the trick. If you keep on reducing this, you reduce this further, Now also you have different direction of velocity, this one and this one. Here also this one and this one. If you keep on reducing this, a time will come when this point will reach here and there is going to be only one direction of velocity. Okay? And there you will say that it is perpendicular to link 2 as well as it is perpendicular to link 3. That means this is going to be I23, this is going to be I12 and this is going to be I13. So that's for sure. So this is only possible if there are three links which are connected to each other and they're moving with respect to each other, sort of making motion. Then there are going to be three eye centers and all of them are going to lie on a straight line. Unless, so velocity cannot have two different directions unless I23 lies on a line joining what? We're going to check that out once again. Joining I12, I13 and I13. So there is a broader application of eye center. We'll see that when we try to solve the problems. Okay. Now the most important section of today's video, that is the general procedure. Let's take a look at this. So basically, to understand the general procedure, we've got 5 steps. Not even 5, but 4 steps to be very precise. And for that, let us try to make a 4-bar mechanism. This is going to really help us. Okay. Let's say we've got a link which is fixed. Let me call that as link number 1. Right. Then there is this link over here. Let me make this very small. Like here. Okay, this way. So basically this is 1, link 2, this is link 3, this is going to be link 4. And let us mark these endpoints as A, B, C and D. Fair enough? Okay. So the first thing that you need to do is you need to count the number of links. Okay. Or rather I should say this, find n, not small n, but capital N. N is equal to n minus 1 by y2. And if you just punch in the value of n for a 4-bar mechanism such as this, the value of 4 minus 1 is 3, 3 into 4, 12, this is going to be 6. Now we know that there are going to be 6 eye centers. Now try to make a list. Step 2. In step 2, what we'll try to do is we'll try to make a list of eye centers. Make a list of eye centers. Okay, so just try to follow this table. Write 1, 2, 3 and 4 and then start making combinations. Okay, let's start from here. Let me use a different color. 1 with 2, 1 with 3, 1 with 4. 2 with 1 is done. So 2 with obviously 3 and 2 with what? 4. Well, 3 with 1 is done, 3 with 2 is done. So 3 with 4 is left and we have nothing to follow. Okay, so there are 6 eye centers, 1, 2, 3, 4, 5, 6. How do we place them one by one? That is something which we need to see. Okay, fine. In step 3. So in step 3, what you need to do is you need to locate the permanent eye centers. Not permanent, but fixed ones. Let's start with. Step 3. Locate permanent and fixed eye center. Locate permanent P and fixed F eye centers. Shortcut. Okay. How? By visual inspection. By visually inspecting. This is fairly easy. So here link 1 and 2. Okay, a pin joint, and this is I12. Link 1 and 4. This is I14. This is I23 and this is I34. Very easy. Done and dusted. So 4 eye centers have been located. Okay. Step 4 is a bit tricky. In step 4 we need to find those I centers which are neither fixed nor permanent. This is a bit tricky. Step 4. Step 4 is for location of neither permanent nor fixed I centers. Let me write this clearly. Neither fixed nor permanent I centers. Nor permanent I centers. Okay, now this can be achieved using circle method or circle diagram. Circle diagram. So let me just demonstrate how this can be achieved. It's very easy. And once you locate all the I centers, then the remaining stuff is very easy. The velocity calculation, be it the linear velocity or the angular velocity, all of them is pretty easy. And for that, a bit of angular velocity ratio theorem will also be used. Okay. Now, using this circle method, let me just draw a circle. Okay, fine. Let me draw a perfect circle. Yeah, will do the job. Now, just take a careful look. Let me just mark points over here. Let's start from here. Let's say this is 1. Let's say this is 2. That's 3. And let's say this is 4. Right? Let's join 1 with 2. So I center 1, 2 has already been located. 1 with 2, make a circle. 1 by 1 we'll circle. Okay? 1, 2. Then 2, 3. 2, 3. Where is 2, 3? That's it. That's 2, 3. Then 3, 4. Fair enough. 3, 4. Where is it? 3, 4. So these are all the permanent and fixed I centers. Very easy to locate. And then there is this 1, 4. That's 1, 4. The problem is with this 1, 3 and 2, 4. And these two I centers are of what nature? They are neither permanent nor they are fixed. And they are going to vary with the mechanism. Okay, how can we locate them? Let's say we want to locate I center 1, 3. So just join 1 with 3. Now this 1, 3 is actually a part of this triangle 1, 2, 3 and also a part of triangle 1, 4, 3. Let me repeat. Okay, let me erase. Let's say we want to locate this I center 1, 3. So join 1 with 3. Fair enough. Now this line 1, 3 is a part of triangle 1, 4, 3 and it is also a part of triangle 1, 2, 3. Just let us now talk about, rather focus on this triangle. Okay. So one portion is 1, 3. The remaining portion is 1, 4 and 4, 3. Now draw a line passing through I centers 1, 4 and 4, 3. Simply just extend. Just extend. This way. Done. So this has been taken into the picture. Now what? Okay. Another triangle is this one. 1, 2 and 2, 3. 1, 2 and 2, 3. 1, 2 and 2, 3. Draw lines. Extend lines. Let me do it. Very pathetic drawing skills. Okay, so that's the I center. We've got this. What have we got? We've got I 1, 3. Achieved. Now what? Now we want to locate. Okay, let me circle this. I 1, 3 achieved. Okay, so one of the neither fixed nor permanent I centers have been located. We want I 2, 4. This way. So I 2, 4. Just take a careful look. 2, 4 is a part of triangle 2, 3, 4. Also a part of triangle 4, 1, 2. 2, 3, 2, 3, 4. 2, 4, 2, 3, 3, 4. 2, 3, 3, 4. Where are we going? 2, 3, 3, 4. 2, 3, 3, 4. This way. And so 2, 4, 2, 3, 3, 4 and 1, 4, 1, 2. 1, 4, 1, 2. This way. 1, 4, 1, 2. Just extend. And here we go. That's the I center I was talking about. And this is what? I 2, 4. So all the I centers have been located. Very easy. Okay. And this right here is a circle diagram. And this is something which I appreciate that you guys would be using. Very, very important. Okay. Your marks won't be cut in the examination. If you don't draw this, but still, I would recommend you guys to draw this. Right? Okay. Now the one thing which is left is angular velocity ratio theorem. Let me just try to explain you. Let's say, how can I say this? We know omega 2. We know this. Let's say we want to calculate omega 4. So how can all of this concept be applied? If we know the value of omega 2, how can omega 4 be calculated? This is something which can be achieved using the angular velocity ratio. Very easy. It's very easy. And I'll tell you in much more detail in the problems to follow in the upcoming videos. But right now, let me just give you a snapshot as to how this angular velocity ratio can essentially be applied. For that, I need to rub a lot of stuff. Here it is. That's done. Okay. So remember the steps. You start with calculating the number of links, not number of links, but the number of I-centers, and which has been followed by the making a list, then which is followed by locating the fixed and permanent I-centers with the help of inspection simply, and then finally using the circle method to work out the neither fixed nor permanent I-centers. Once that is done, you just need to apply the angular velocity ratio theorem to compute the value of omega, and similarly you can also calculate the value at any given point, okay, or the linear velocity, right? How can that be achieved? Angular velocity ratio theorem. This is not exactly a theorem, but this is more in the mathematical sense. Let me tell you what that is all about. Okay, so what we are essentially trying to do is, we have been given omega 2, that is the angular velocity of link 2. This is known to us, angular velocity of link 2. What we want to find is the angular velocity of link 4. Okay, angular velocity of link 4. How can this be achieved? Let me tell you. Okay, so this is a line diagram basically. Originally the rigid bodies are not like this. The members are not like this. Anyway, let us get back to the topic. Let's say, let me make any random plane figure. Okay, let's say link 2, this link 2 is extremely big. This is link 2. It is extremely big. And big to such an extent that I center 24 lies somewhere here. This is I24. Okay, and this link is actually rotating about point A. So there is this point A, right? So this link 2 is what? This is actually rotating with an angular velocity what? Omega 2. So if I were to calculate the velocity at this point, okay, let me just write this properly. This is I24, isn't it? If I were to calculate the velocity at this point, the velocity of instantaneous center 24, this is perpendicular. V24 can be written as V24 is equal to angular velocity, okay, that is omega 2 multiplied by radius. We know this formula very well, very fundamental. V is equal to omega r, and this is what we are going to calculate. Now, V, velocity of a particle at instantaneous center I24, or simply the velocity of instantaneous center 24. V is equal to omega r. So this I center is on this link 2, fair enough. Okay, so it is going to have this angular velocity omega 2 multiplied by the radius. This is the center of rotation and this is the instantaneous center. The distance between the instantaneous center and the center of rotation is the radius. So this is going to be how much? This is going to be I24 minus this, what? This is what? I12. So let me just write this as I12. I12. Okay, so this is one way of looking at this, applying the angular velocity theorem. Ratio, what is the ratio? Okay, let me talk about that also. Okay, let me just rub this off. Again, try to focus. I24, link 2 and link 4 have the same center of rotation at this instant of time. Link 2 and 4. And let's say that link 4 is extremely big. Link 4 is extremely big, and this is the center of rotation of link 4. Okay, this is point D, and this is basically I14. And far away on the link, we have got this point. The point's name is I24. Now this link is actually rotating with angular velocity. Since this is link 4, so therefore the angular velocity is omega 4 and the linear velocity is going to be v24. Okay, so again this is fairly easy. v24 again can be worked out from considering this link 4. We are now taking into the picture link 4. The same velocity can be calculated now using link 4. So v24 can be written as v24 is equal to now omega 4. This is going to be omega 4, okay, into r. R is nothing but this is the point where the velocity you are calculating, and this is the center of rotation, I24 minus I14. I24 minus I14. And once you divide these two equations, the ratio is a mathematical expression, and that is in fact the angular velocity ratio theorem. Let me just divide these two and this is going to cancel out. Ultimately the equation which you are going to get, one is going to be equal to W2, not W2 but omega 2 by omega 4, and this ratio I24 minus I12 whole divided by I24 minus I14. If we just try to do the swap, omega 2 by omega 4, what we needed is omega 4. Okay, anyway, let me just write this in a much more simplified form. Omega 4 by omega 2 is equal to I24 minus I12 whole divided by I24 minus I14. Okay, so that was the expression, final expression which expresses rather the angular velocity ratio theorem. So guys, that was all for today, and in the upcoming videos we'll take up a lot of problems from I-center method. I've planned as many as 4 different problems, and the animations of 2 of those have already been made. Excellent animations. Okay, you'll really appreciate my work. So guys, that was all for today. I'll see you again in the next video. Until then, take care, have a nice day, and keep learning, keep watching. Thank you.